Today's lesson is on gravity and motion. We already talked about gravity, but we're now going to see how gravity and motion are related. And we're starting with an example. Let's say that you go to the top of a building and you drop a bowling ball and a marble at the same time. Which one is going to hit the ground first? Well, from our everyday experience, you'd probably say the bowling ball. Okay? But different scientists have looked at this question a little bit differently in the past. Aristotle would pretty much agree with what you would think. Aristotle would say the bowling ball hits first because it has a greater mass. Galileo, though, came along a little bit later, and he disagreed. He thought the acceleration due to gravity is the same for all the objects, so they would hit the ground at the same time. Well, okay, let's see, what if we actually did it? Okay, and Galileo did some stuff where he took cannonballs and dropped them from the Leaning Tower of Pisa, or that's the rumor at least. So if I have a 20-pound cannonball and a 10-pound cannonball, and I drop them from the Leaning Tower of Pisa, okay, will the 20-pound one fall in half the time, like Aristotle would say? No, probably not. Would the 20-pound and the 10-pound hit the ground at the same time, like Galileo would say? Well, probably not either. Okay, so which one is right? They both kind of don't really fit with what we see in real life. The reason for that is because of the air resistance. But really, Galileo is correct. Okay, they are falling at the same acceleration. It's just the air resistance gets in the way. And we're going to do a demo in class tomorrow with a guinea and a feather. A guinea is just a kind of a heavy British coin, and then a feather is very light, obviously. And you can see in the picture what's basically going to happen. We'll put them in a vacuum tube and we'll suck out the air, and then we'll really see the difference between what Aristotle and Galileo thought. And like I said, Galileo is going to be turned out to be correct, that things do fall with the same acceleration. Now, I still have a little bit of a problem with that, understanding it, and it's kind of hard to understand. Acceleration depends on force and mass. A heavier object experiences more gravitational force than a lighter one. So why doesn't that heavier object land first? If I have this 20-pound bowling ball up here and a 10-pound bowling ball over here, the 20-pound one has more gravity. Okay? It has more force pulling it down than the 10-pound one. So shouldn't it fall faster? It has more gravity pulling it down. Okay, that's where it's kind of confusing. It doesn't because of something called inertia. A heavier object has more mass, and because of that, it has more inertia. Inertia is an object's resistance to changing motion. Okay? A heavier object is harder to accelerate because of its greater mass or inertia. That extra mass and inertia exactly balances the additional gravitational force. So the acceleration of gravity is the same on every object. Let me try to say that again. Our heavy bowling ball here, 20-pound bowling ball, okay? It is harder to accelerate because it has more inertia. Okay? Imagine if it was sitting on the ground and you came up and you tried to kick it. Okay? It would be harder to get it accelerating than the 10-pound one because it has more inertia. Okay? The more inertia an object has, the harder it is to get it to change its motion, to accelerate it. Okay? So yes, the 20-pound one has more gravity pulling it down, but it also has more inertia preventing it from accelerating. That extra inertia exactly balances out with the extra gravity, so all the objects do fall with the same acceleration. And again, assuming no air resistance. Okay, and we'll go over that again in class. Remember, acceleration is the rate at which velocity changes over time. All objects accelerate towards Earth at a rate of 9.8 meters per second squared. And we're going to see that calculation coming up. The key thing, though, is this 9.8 meters per second squared for Earth. we are going to use this number a lot, okay? Because we're on Earth, okay? When we drop objects, when we throw objects, we're on Earth, so we're going to be using this acceleration of 9.8 meters per second squared down. So for every second an object falls, its velocity increases by 9.8 meters per second. And we'll look at this on the next slide. So here we have a ball, and it starts off at 0 meters per second. Okay, so we just drop it. In the first second, it's going to fall 4.9 meters, but it's going to be going 9.8 meters per second downward after that first second. It's going to keep falling. After the second second, it's going to be 9.6 meters per second downward for a velocity. After the third second, 29.4 meters per second downward. So it's going to keep on accelerating faster and faster and faster and faster and faster. It's getting faster, faster, faster. Okay? The acceleration is 9.8 meters per second per second. So every second, it's getting 9.8 meters per second faster. And again, normally we would write that 9.8 meters per second squared. Okay? So the acceleration is 9.8 meters per second squared. Okay, that's a very easy relationship. We can have a formula that will show that. Again, this is on Earth, right? 9.8 meters per second squared on Earth. If we were on the moon, it wouldn't be this number. It would be a lot less because the moon has less mass than the Earth, so the moon has less gravity. So it's going to pull a lot less force. Also, of course, on Earth, we have air resistance, which is going to change this. So this 9.8 meters per second squared is in an ideal perfect Earth, okay, with no air resistance falling straight down. Okay, like I said, on the moon, it'd be a lot lower, and there is no air resistance. We'll actually watch a video clip of Apollo 15 where they dropped a hammer and a feather, and we'll see them accelerate more slowly, and we'll see them hit the ground at the same time. Okay, like I said, it's a perfect relationship, so we have a formula. And you've already done some work with this formula. Okay, the velocity of a falling object equals the acceleration due to gravity, 9.8 meters per second squared downwards on Earth, times the time that it's falling. Okay? If the object starts at rest, the equation will give us the velocity after a certain time period, like when it hits the ground. So we'll do one quick example because you've already done some. You drop an egg from a bridge. What's its velocity when it hits the ground 3.0 seconds later? So velocity equals g times t. The g is going to be our 9.8 meters per second squared because we are on Earth, times our time, which is 3.0 seconds. Okay. I multiply that out, and I get 29.4. Okay, what's my unit label? Well, I had meters per second squared times seconds. The seconds will cancel out with one of those, so I end up having meters per second. Okay. Don't forget my direction, which is down. And then I need to check for significant digits. 9.8 had 2, 3.0 has 2, so my answer can have 2. So that's going to round to 29 meters per second downwards. Okay, so the egg will be hitting the ground going 29 meters per second, assuming no air resistance again. Okay. So now again, we're getting into this idea of air resistance. So let's say I drop a book and a sheet of paper at the same time. What will happen? Okay, again, you obviously know the book is going to hit first, right? We're going to do some demonstrations in class, and we're going to see if we can get it at least a little bit closer, get that sheet of paper falling a little bit more closely. Could we, in class, have the paper and the book fall at the same time? Maybe so. Like I said, we're going to try that in class. But the reason, again, that they don't hit the ground at the same time is because of air resistance. It's causing the piece of paper not to accelerate as fast as the book. What is causing the air resistance? It's a force you already know. Simple answer is friction. Okay, friction is what causes it not to accelerate. at the 9.8 meters per second squared. Now, friction between what? Okay, well, it's friction between air molecules and the object. So as the object falls, the air molecules are going to brush up against it, causing friction, slowing the object down. And we'll look at this on the next slide, and it'll show an apple. So there's my apple. And the apple is falling with the force of gravity, trying to accelerate it at 9.8 meters per second squared. So this green arrow, this long green arrow or green vector, is the force of gravity, trying to accelerate it at 9.8 meters per second squared downward. Well, there's air, and the air is rubbing up against the sides of the apple, rubbing up against the sides, rubbing up against the sides. Okay, so the air is constantly rubbing against the sides of the apple, causing friction, which is a force, and it's slowing it down. So this purple arrow is that force of air resistance. If you remember when we did our net forces, you subtract the two forces if they're going in different directions. So we subtract the green arrow and the little purple arrow, and we get this, our net force. Okay. It is still downwards, obviously. So that apple will accelerate as it falls. It just won't be at the 9.8 meters per second squared. Okay, but it will accelerate as it goes down. Now, how fast will it get going? That's going to depend on a lot of things, but that's called terminal velocity. Okay, terminal velocity is going to basically be the fastest that an object is going to fall because air resistance balances out the force of gravity. Okay, and let's think about that. So if we go back and we had our apple, if it fell faster, 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 there'd be more and 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 more air resistance. And this purple arrow would get longer, 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 until the purple arrow was the same as the green arrow. If they were the same length, same quantity, we wouldn't have, or would they be balanced? There wouldn't be a net force. So it wouldn't accelerate anymore. And whatever speed that it was going at, that's the speed that it would continue to go at. Okay, we're going to finish terminal velocity in part 2, and we're going to compare it to free fall.